Okay, so now we are going to look at using the Fourier transform to solve the diffusion equation. So the diffusion equation is the t derivative of u is equal to the double x derivative of u. So the diffusion equation says the t derivative of u is equal to the double x derivative of u. Okay, so this is going to be reminiscent of how you use Laplace transforms to solve ordinary differential equations. In particular, you're going to have step 1, take Fourier transform of the equation. Step 2, you're going to solve, so you're going to take the Fourier transform of both sides. You're going to solve for u hat. The difference is that going to be, the difference for Fourier transforms is that instead of there being an algebraic equation to solve for u hat, we're going to solve a differential equation, which several of you have noted in the comments already. And 3, find the inverse Fourier transform of u hat. And there's several ways of doing this. Really, there's a best way. I guess is the way that I'm going to do it. Okay. So let's see if I can use a different color here. I like purple. All right, so we're going to start by taking the Fourier transform of both sides. Now, the thing that I want to point out is that we are taking the Fourier transform in the x variable. In other words, as far as t is concerned, as far as omega is concerned, t is a constant. So the Fourier transform of the t derivative of u is equal to the t derivative of the Fourier transform. And if you're not convinced by that, I'm going to do this computation here. So the t derivative of the Fourier, this is the Fourier transform of the t derivative of u. Just by definition, this is 1 over the square root of 2 pi times the integral y equals minus infinity to positive infinity, the t derivative of u evaluated at xt times e to the minus I omega x dx. Now, assuming everything is nice, which is what we're assuming about this, in other words, our functions are integrable. Our t function is absolutely integrable. Or our u function is absolutely integrable. The differentiation is with respect to t. This should say y, x equals 0. The integration is with respect to x, and the boundaries don't depend on t. So we can interchange the differentiation and the integration. So this is now going to be the partial derivative with respect to t of 1 over the square root of 2 pi times the integral x going from minus infinity to positive infinity u of xt e to the minus I omega x dx. But inside the brackets there, this is just the Fourier transform of u, and we're taking the t derivative of it. Okay, so this shows the Fourier transform of the t derivative is the t derivative of the Fourier transform. Okay. And that's because we're taking the Fourier transform in the t variable. All right, in the x variable. So the Fourier transform of this is going to be the t derivative. I'm going to use a subscript notation. Okay, the Fourier transform you had is a Fourier transform, then we take the t derivative. And on the left-hand side, remember the Fourier transform of the x derivative is I omega times the Fourier transform of u. So it's going to be I omega times I omega, that's minus omega squared times the Fourier transform. And I'm pretty sure this was an example we did in one of the previous videos. Well, this now, if we think about omega as being fixed, this is a differential equation, an ordinary differential equation in the t variable. So if I just solve this, I'm going to get u hat of omega t. This is an ordinary differential equation. Omega is a constant. Imagine that omega is 17 or something. We have the t derivative is equal to minus 17 squared times the function. Okay, so it's of this format here. Y prime equals minus omega squared y, where y is a constant. We know the solution is going to be, if our variable is x here, is going to, instead of t, is going to be y of x is equal to y of 0 times e to minus omega squared x. Now we're going to have something similar, except instead of x being the independent variable, t is the independent variable. So this is equal to u hat of omega 0 times e to the minus omega squared t. Okay, and I've done this twice already, so I'm not going to redo this. I meant to say up here, in addition, let's assume we know that u of x0 is equal to f of x, just so we have something to write down. So then, if u of x0 is equal to f of x, this right here is just the Fourier transform of f. And so this is f hat of omega times e to the minus omega squared t. So u hat of omega t is equal to f hat of omega times e to the minus omega squared t. Okay, so we just did step 2. We solved, this should say solve for u hat. We just solved for u hat. Again, very similar to, structurally it's very similar to Laplace transforms. We're using Laplace transforms to solve ordinary differential equations. The difference is that when we use Laplace transforms to solve ordinary differential equations, 2 was typically an algebraic equation instead of a differential equation. But here it's a differential equation. Okay, I'm going to erase this part right here and just write the Fourier transform of u. Okay, so we've got the Fourier transform. The Fourier transform of u is equal to f hat of omega times e to the minus omega squared t. And now what we want to do is we want to find the inverse Fourier transform of that. Okay, and for that, we're going to use this convolution fact. So remember that if we have 1 over the square root of 2 pi times a convolution of f and g, 1 over the square root of 2 pi times a convolution, the Fourier transform of that is equal to f hat of omega times g hat of omega is equal to f hat of omega times g hat of omega. Now what I fear some of you might be doing in solving this, so a lot of you will realize that we need to find the inverse Fourier transform of this. I'm fearful that a lot of you are going to be saying that the inverse Fourier transform, you're just going to take this and plug it into the inverse Fourier transform integral. I don't want you to do that because that's going to give you something that's going to give you something that is not sort of the standard way, and is not an easy way to think through solutions to this equation. It's obviously not technically wrong, okay, but it's just not the best way to write the solution. The other problem with that is that you're going to, for the next problem, when you add a term to that equation, like a plus c times the x derivative of u, now you're going to be dealing with even more complicated things. Okay, so I want to use this convolution here, but to do that, I need to figure out what the inverse Fourier transform of e to the minus omega squared is. Well, we already did this in a previous class. We showed that that if you look at e to the minus x squared over 4t divided by the square root of 2t, the Fourier transform, so the wiggly line here means the Fourier transform of this is equal to e to the minus omega squared t. Okay, so the inverse Fourier transform of e to the minus omega squared t is equal to this guy right here. Okay, so, all right. If I look at this formula here, f hat and f hat kind of match up with each other, and g hat of omega kind of matches up with this. And so the inverse Fourier transform of this, which is going to be the solution, the inverse Fourier transform of this is going to be the convolution of f, and the inverse Fourier transform of e to the minus omega squared. And divide that by 1 over the square root of 2 pi. So, computer's doing that annoying thing again. Okay, so u of xt, is going to be 1 over the square root of 2 pi times a convolution of f and g, where g is this function here. Okay, g hat is this function, which means this is g. So it's going to be the integral y going from minus infinity to positive infinity, f of y, and now it's going to be this, but instead of having an x, it's going to be evaluated at x minus y. So this is e to the minus x minus y squared over 4t over the square root of 2t dy. So I'm going to rewrite this slightly. Basically, I'm just going to move this square root out in front of the integral here. So when I do that, I get the following. So u of xt is equal to 1 divided by the square root of 4 pi t. There's a 2t and a 2 pi, so the square root of 2t times the square root of 2 pi is the square root of 4 pi t. And then I'm writing the integral sign. We're going from minus infinity to positive infinity, and the function we're integrating is f of y. That's what I'm attempting to write now. And then times an exponential function, and the exponential function is going to be minus x minus y squared divided by 4t. 2t. Wait, no, I forget, is it 4t or 2t? Yeah, this is one of those things where I'm confident that it's 4t, but now I am losing my confidence. Yes, 4t. Okay. 4t dy. And this is the solution to the diffusion equation if u of x0 is equal to f of x. Notice if we didn't want to like explicitly state this condition here like I started with, instead of having f of y, we could have something instead, u of y0. But technically, not technically, but typically it's good if we specify u of y0. We'll look at an example when we specify a certain u of y0. So I'm just going to put this back. I'm going to put this back as f of y. Okay, f of y would correspond to like the initial temperature distribution or the initial concentration distribution of whatever it is we're studying. Okay, so this is using Fourier transforms to solve the diffusion equation. Like I said, please, the reason, yes, it is correct to do the inverse Fourier transform of this. The problem is that instead of having f there explicitly, you have f hat there explicitly. If you write f hat, if you then write the integral formula for f hat to get f there explicitly, you have a double integral instead of a single integral. Okay, unless you basically just go through the proof again of the inverse Fourier transform. So do it this way right here. I didn't specify it in the homework, but I should have because I forgot about this one point of confusion or whatever, or not confusion, but point of, I don't know, my lack of clarity or detail or my lack of giving, well, whatever. It should be this right here. So anytime you can write an answer with one integral instead of two integrals, that's typically going to be the best. Okay, so that's it for this equation. In the next video, we're going to look to see what happens for a particular value of f. Then we're going to get some properties of solutions to the diffusion equation, and then we'll look at solving more complicated diffusion style equations.